So the next speaker is Oliver Dyer from IBM. So he's going to talk about some issues of superconducting quantum computing, some challenges and opportunities. So Oliver, could you present your talk?
Before I begin, I'd like to thank the organizers for giving me a chance to speak to you all today. It's difficult to organize an event like this at the best of times, and especially right now, I know it's quite a bit of trouble. So thank you very much for making the effort. Today, I'd like to talk to you about improving the performance of IBM's quantum hardware. I'm going to begin by giving you a quick overview of what IBM's architecture looks like for our qubit chips themselves. And then I'm going to talk to you about two different ways that we're trying to improve our devices. The first of which is increasing the total number of qubits, which presents a series of interesting engineering challenges. And the second thing is improving the quality of the qubits themselves. And specifically, I'm going to be focusing on the quality of our 2-qubit gates today. IBM's quantum computers are based off of a type of superconducting qubit called the Transmon. These devices look like a capacitor, pretty small one, about 60 femtofarads, that's been shunted by a Josephson junction. And the limit that we build transmons in, that Josephson junction is always going to be sitting at the bottom of one of its wells in the current phase relationship. And so we could basically think about it as acting like a nonlinear inductor. We control the frequency of our qubits by controlling the size of that capacitance and the critical current of the Josephson junction. And we'll typically choose it to have a frequency of about 300 megahertz. The fact that the Josephson junction acts like a nonlinear inductor gives us a slightly different energy spacing between the 0 to 1 photon transition and the 1 to 2 photon transition in our devices. And we'll choose that difference to be about 300 megahertz. That's large enough that we're going to be able to easily isolate the 0 to 1 transition from the rest of the excitation manifold of our devices, but small enough that we're still reasonably far deep inside of the Transmon limit for these devices. Our Josephson junctions are going to turn out to typically be about 100 nanometers on a side, and we're going to make our capacitors out of superconducting metal on top of a silicon chip surface because we know how to do complicated semiconductor processing on silicon relatively easily. Those capacitor paddles are going to be a couple of hundred microns on a side in our typical devices. Now, there's a common misconception that that's because our transmons have to act like microwave antennas, but for the kind of 2D geometry I'm talking about, that's simply not the case. However, it is true that the larger we make our transmons, the more we spread the electric field associated with them through space. And what that does is puts a smaller fraction of the electric field inside of thin, lossy interfaces. For example, the thin oxide interface on top of our silicon chip itself, or on top of the niobium that we make our capacitor paddles out of. Now, of course, it does us no good to have a qubit if we don't have a way to control it. And the chief mechanism that we give ourselves to control this qubit is coupling it to a CPW-made resonator. And this resonator will typically have a frequency of about 7 gigahertz in our devices, and it serves three chief roles. First of all, because it's off resonance with the qubit, what it's going to do is tend to prevent the qubit from decaying by emitting a photon back out of its drive line. We call this kind of protection cell protection, and in fact, in our more advanced devices, like our commercial devices, this resonator is in fact a many-pole filter to try to keep that from happening even as we couple the resonator more and more strongly to the qubit. Secondly, the resonator provides us a way to measure the state of the qubit. And the reason why we do that is because the resonator is coupled to the qubit. It's going to turn out that its resonant frequency depends very slightly on the state of the qubit. And so by performing a fast measurement of the resonator's frequency, we can perform a fast measurement of the state of the qubit. Finally, we can drive single qubit gates on our qubit by applying microwave pulses to this resonator that are resonant with the qubit itself. Now, when we do this, we drive Rabi oscillations. We'd have to use relatively high powers because we're, of course, driving off resonantly through this resonator. But this gives us our main means of single qubit control. And the basic means for doing this with high fidelity have been established for many years. We'll typically use what's called a drag correction, which involves adding a very small amount of the derivative of our pulses back into the control tone itself. And that will both correct for small z errors because our qubit is not a perfect qubit, but rather this anharmonic oscillator. And it also turns out to correct for dispersion in the cabling that we have going down to the qubit itself. For 2-qubit gates, we use a technique called cross-resonance. And here we're going to talk about 2 qubits, one on the left that we'll call the control, one on the right that we'll call the target. And we're going to exchange couple these together by capacitively coupling them either through a resonator or just through a chunk of metal. This exchange coupling is going to hybridize the 1-0 and the 0-1 states of the 2-qubit system. But critically, the sign of this hybridization is going to change depending on the state of the control qubit. So 1-0 plus J over delta, where J is exchange coupling, delta is the detuning between the qubits times 0-1, or 0-1 minus that same term. What this means is that if we drive the control qubit at the target qubit's frequency, we're going to be driving the target qubit through this small amount of hybridization. And so we're going to get a rotation that depends on the state of the control qubit. So the exact speed of the rotation on the target will depend on the state of the control. Now, at the same time that we're doing this, there's a lot of other complexities that are going to happen, including unconditional X rotations, ZZ interactions from the fact that these qubits frequencies now depend slightly on the state of the other qubit, all kinds of fancy things that we have to be clever about refocusing away or actively canceling out. And one of my colleagues, Peter, is going to be talking about this, I believe, later today or possibly tomorrow, some of the improvements that we've made in how we refocus these cross-resonance gates recently. Now, when we put all these together, you get something that approaches our current state-of-the-art IBM quantum processors. And here's a picture of, for example, our Falcon R4 processor on the left. This is a 27-qubit device, and you can see all kinds of metrics down below, T1s, T2 coherence times, single qubit gate errors, 2-qubit gate errors, readout errors. This is a big stack of metrics, and even these don't really capture the full performance of the device because we've left out things like idle couplings that cause qubits to accumulate errors when we do nothing to them, crosstalk errors when we're driving gates. Really understanding the quality of a complex quantum system is pretty tricky. We like to use a metric called quantum volume to describe the performance of our processors. And one way of thinking about this is as sort of a game. One person provides a circuit that consists of layers of random 2-qubit operations between pairs of qubits, with all the qubits active in every layer. There are n layers in this circuit, and there are n qubits in each layer. We say that a processor has passed at quantum volume 2 to the n if it's able to run that circuit and get the right answer more often than not. Now, there are a couple of reasons we like this. One is it's very hard to game. It requires that you run a circuit that somebody else provides. You don't get to pick what circuit you ran afterwards. And so it looks kind of like running a quantum algorithm that gives you an answer that you care about. It doesn't give you any advantage for adding more and more qubits if those qubits are low quality. And similarly, there's no advantage to having extremely low error rates if you can only do it on a couple of qubits. And so we feel like this quantum volume metric does a pretty good job of measuring how well your quantum processor is able to solve real problems. Now, we've been tracking the quantum volume of our devices for a number of years, from 2016 to 2020. And these improvements that we're seeing here as we go from not measured up to QV64 quite recently reflect improvements of the compiler, because we have to map that complicated circuit to our real device, improvements in our 2-qubit gate fidelities, and our state preparation and our measurement, and really everything about our device. Interestingly, we're not the only ones measuring quantum volume these days. Rigetti and Honeywell measure it. IonQ has indicated they'd like to measure it. And in fact, right now, Honeywell has just recently announced a QV128 on one of their trapped ion processors, which is a really nice achievement. Obviously, I still think the superconducting processors will do a little better in the long run, but it's a real horse race. So we've got this quantum volume. We want to get it up. How are we going to improve our devices? Well, there's two basic ways we need to improve. We need to add more qubits. Not so much because that's a limiting factor for quantum volume right now, but because we know as we add more and more qubits that we're going to face engineering challenges. They're going to be tough to solve. And so if we don't work on solving these challenges right now, we're going to be stuck when it actually becomes important. And the second thing we really want to do is give ourselves better qubits. And really the limiting error rate on most of our devices is a 2-qubit error rate. So here you see a map of the average C0 error rate on various commercial devices we've released over the past couple of years. You can see that getting better and better and better. But we really want this to get enormously better. We'd like to be down in the 10 to the -4 range, where we can create an error-corrected quantum processor. So let's tackle more qubits first. This is our current roadmap for number of qubits. You can see each year we're trying to roughly double the number of qubits. These kind of funny numbers come from specific code depths in a heavy hex error correcting code, which is where we'd like to go in the long run. And the key thing here is each one of these numbers, it indicates a specific engineering challenge that we need to tackle and surpass to get to that next size processor. So don't so much think of this as just a progression of number of qubits, as think of it as a progression of engineering challenges. To get to 65 and 27 qubits, our most recent couple of devices, our big achievement was breaking the plane. If you imagine a dense crowd of qubits, you can't route signals to the innermost qubits on a strictly 2D device. And so what we introduced was a bump bonded flip chip technology that gave us basically two wiring layers, one for the qubits and the other to deliver signals into the device on. This is what we're using in our Falcon and Hummingbird, the 27 and 65 qubit devices. But there's two big limitations to this bump bonded approach. One is that we run out of perimeter to escape the signals pretty quickly as we make this device larger and larger. This perimeter is proportional to the square root of the number of qubits, not the number of qubits. Secondly, as we reach deeper and deeper into the chip on this simple flip chip technology, we run into more and more crosstalk associated with these long parallel runs. And so we wanted a way to get around both of these difficulties. So what we're introducing at our next generation of devices is superconducting multi-layer wiring. And this is basically conventional back end of line CMOS wiring, except now instead of using a normal metal, we're using a superconductor, niobium, in fact, to construct the wiring. And so what we're building right now, it has 3 layers of metallization with a pattern planarized oxide between the levels. This gives us a way of making well-isolated transmission lines, like this guy in the center. If you follow around the outside edge, you'll see a complete ring of niobium. There's a via that you can't see because it's buried deeper inside of the page through this cross section. We have buried vias to connect the different metallization levels. And of course, top level vias to connect the second and third metallization level. Now, it does us no good to build a complicated structure like this unless we can confirm that it's superconducting. And so here, what we're looking at are measurements of a 12,000 via chain through this superconducting multi-level wiring. So here we're going from the top niobium level down to the second, down to the third, and then back up again for 12,000 vias in total. And what you can see is that we do indeed go superconducting. You can see 3 distinct different transition temperatures, which correspond to these 3 different layers that each have a slightly differing amount of damage done to them by the subsequent processing. We can also look at the microwave characteristics of this. So here what we've done is we've constructed a strip line that is roughly 20 feet long, has an electrical length of roughly 20 feet on a single chip. And we're looking at a TDR measurement down this transmission line. And so what you see is our 50 ohm feed line coming from the outside world, our wire bonds to get onto the chip itself, 20 nanoseconds of our 30 ohm strip line, and then finally a second wire bond at the end going back up to our 50 ohm outside impedance, showing that the signal escaped on the other end successfully. So we built the superconducting multi-level wiring. We know that it's superconducting. We know that we can transmit microwave signals through it with high fidelity, and we can yield very, very long lengths of it. The next step is going to be to integrate this with qubits, and that's something that we're doing right now and we'll probably be talking about at the March meeting. Now, our second big goal is to give ourselves better qubits. So here's 2 different views of our qubit error per gate. On the left, we look at the average C0 error rate for our devices, dropping slowly as a period of time. On the right, we're looking at the distribution of the error rate for the devices. And what you see is that in our most recent devices, what we've been doing is not so much improving the best gates, is taking the gates and making them much, much more uniform. And I'd like to talk for a moment about how we accomplish that before I talk about what one of our next steps might be. Now, recall that in cross resonance, we drive a gate by driving a control qubit at a target qubit's frequency. So in a square lattice, we need each one of the possible target qubits that we might want to manipulate with a control qubit to have a different frequency. That means we need to have 5 different colors on our lattice if we're going to have no collisions. Now, lots of bad things can happen here. If 2 targets have the same frequency, we won't be able to drive a gate. If the control and the target have the same frequency, we won't be able to drive a gate. If any of these frequencies line up with any number of other transitions in these devices, because remember, these are anharmonic oscillators, they've got all kinds of levels associated with them, then we're going to drive leakage transitions. Of course, none of these collisions ever happen exactly. There's always missed by a little bit. And so we can compensate to some extent if one of these things happens by driving the gate slower, but you pay a penalty in the fidelity of the gate when you make that choice. So in our devices, we choose the qubit frequency at fabrication time, basically with the critical current of that Josephson junction. It's not something that we control terribly well. So this is the main fallout on our square lattice devices for both low gate fidelities and yield as a whole. So if we could find a way to color this lattice with fewer than 5 colors, we would expect to be able to avoid these collisions by more. And so we would have fewer collisions and higher fidelity gates on average. So the way we do that is by going to a topology we call the heavy hex. And one way of thinking about this is that we take that central qubit and we split it in two, and then we insert a third qubit in the middle. Now, the really cool thing about this is if I use, notice that every other qubit only has 2 neighbors, right? We go 2 neighbor, 3 neighbor, 2 neighbor, 3 neighbor. If I use those 2 neighbor qubits as my control qubit, I can color this entire lattice with only 3 colors. And that gives me an enormously less opportunity for frequency collisions and higher fidelity gates. Now, there is a penalty that swaps are needed for some circuits. So there's a trade space here that we've improved gate fidelity, we've improved the reliability of our devices, we've paid a penalty in connectivity that potentially requires more gates. So if the improvement in fidelity exceeds the cost of these extra swaps, we win. Now, whether or not that exceeds the cost depends on the algorithm you'd like to run. In the long, and for some algorithms in particular, for example, error correcting codes, we already have some plans for how we can run these on heavy hexagonal lattices with actually very little additional overhead. So we think that this is actually a really good compromise. Now, the other thing that you can do, instead of changing the topology of your lattice, is to try changing the way that you run your gates. So here is a flux-tunable gate that's proposed by Fei Yan in this paper here. Here we have 3 flux-tunable qubits, or we have 2 flux-tunable qubits and a flux-tunable coupler connecting them together. Now, the really cool thing that he did here was he added a shunt capacitance that bypassed that flux-tunable coupler. Excuse me. And so you basically have 2 coupling paths, a black resonant coupling path and a blue capacitive coupling path. Now, at high frequencies where you're driving that, where the signal is higher frequency than the resonant frequency of that coupler, you get a 180-degree phase shift through it, just like you do with a mechanical oscillator that you're trying to drive too fast. And because of that, there is a magic frequency at which the capacitive coupling and the resonant coupling cancel and give you exactly 0 coupling. So what this means is that you can run a very, very fast gate by shifting your bus frequency around to move between this 0 coupling point and then the nearby very, very high coupling point. Now, we don't love this topology for our devices. We like fixed frequency transmons because they let us get nice long coherence times. And we don't typically make grounded transmons like this. And so what we tried to do was find a way to combine these flux-tunable couplers with the strengths of our qubit designs, with the strengths of our traditional qubit designs. And this is what we came up with. What we've done here is made 2 changes. First of all, we've replaced the qubits with fixed frequency qubits. We're going to manipulate the device entirely by changing the coupler frequency now. That lets us get these longer coherence times. And secondly, because our transmons are typically floating, we can actually couple this bypass capacitor to either straddle of the transmon. If we choose to couple it to the opposite paddle from our resonant coupling, we pick up a minus sign of the capacitive coupling. The reason why this is really cool is this moves the 0 in coupling to be down below the bus frequency instead of above the bus frequency. And so we can now run a gate where we keep the bus below the qubit frequency and then move it left and right between this 0 coupling point and this high coupling point. The reason why this is really cool is by playing below the qubit frequency, we're going to be resonantly interacting with the 1-2 transition of our transmons, which means that we turn on a ZZ interaction very, very sharply as we move this bus coupler up towards the qubit frequencies. And so we can compensate somewhat for the fact that we can't control the qubit frequencies entirely by taking advantage of this much, much stronger interaction that we get by putting the bus down below. So at the bottom left is actually a contour plot here of the coupler frequency on the x-axis versus the detuning between the 2 qubits effectively on the y-axis. And what you can see is over a very, very broad range of detunings between the qubit frequencies, we're able to get quite large ZZ interactions between 1 and 10 megahertz between these devices. So we've tested these on some single 2-qubit devices. We've been able to get down to gate times of 60 nanoseconds, much faster than our typical 220 nanosecond cross-resonance gate time. And we're seeing error per gates of less than 0.2%. So our next step here is going to be to try this on more scaled architectures. And because, it's one thing to show something like this in a 2-qubit device, it's quite another thing to show it in a complex device. And once again, hopefully we'll be able to talk about those results pretty soon. So just to wrap things up, if you want to play with a quantum computer, there's really 2 things you can do. One is you can build a lab like this, and you can build yourself some quantum processors and some control hardware and wire up some fridges and test them. But that's outside of the reach of most of us. And so one thing that I'm actually really proud that we're able to do is to make many of the devices that we're talking about today available either to the public or through partnership programs. And so we call this program the IBM Quantum Experience. So far, we have 160,000 users that have run more than 20 million experiments and written over 200 scientific papers based off of the devices that you can get at through the cloud. So if you want to get started with one of our devices, just go to quantumcomputing.ibm.com, or you can install our Python toolkit, Qiskit. So thank you very much for your time, and hopefully you'll give it a try.
Questions, please feel free to. I think the only way we can do is to write down your questions in the Q&A session. Okay. Since there's no questions from the audience, but actually, I once had a student trying to use in IBM, to do some, this remote experiments, as a virtual experiments, and then we had a difficulty because we wish to have some exercise during the computation. For example, we want to do some measurement. Of course, the machine is so designed that you have the algorithm, you just run this algorithm, then you read out the results. So is there any way to do this so that we can have access during the computation or in the middle steps that we can get some results?
So in parallel to the kind of roadmap that I was talking about on the quantum hardware, we have a roadmap for the control hardware as well. And something that should be enabled very soon actually is the ability to put a measurement into the middle of the computation. And that's going to be followed pretty quickly by 2 different things. The first is we're increasing the readout couplings of our qubits. So we're increasing the qubit to resonator coupling and also decreasing the Q of the resonator so the photons come out more quickly. So that'll let us embed much, much faster measurements into the circuits. Right, currently they take a few microseconds. We want to bring that down to a few hundred nanoseconds. And secondly, the addition of some simple real-time classical processing being possible that would allow things like active state reset or even quantum teleportation or phase estimation type experiments. In fact, on the back end side, that active state reset was turned on recently. So it's a real thing.
Yeah, we'll actually think of some other way to do it, alternative way to do it. We can just say if we want to do the measurement, we basically just need to have this qubit to be swapped or to somewhere, right? So if there's a memory up there, and this could be much cheaper than than the whole processor that you needed to run the algorithm. But of course, if we use the qubits, that's very precious, in the machine. So we will quickly actually just fill all the resources that's available. So if there's some kind of a string of register or memory that can be used, then we can just store that one, and then actually we don't even care about the T2 time, right? So as long as it's kind of measured by the environment, and then what we need to do is just to read out the results, and later on. So this way actually can provide some kind of flexibility for the quantum simulation, algorithms. If there's some cheaper registers available, so that you can dump all the information during the middle steps into those registers.
Yep, that's kind of interesting. I'm trying to think if there are any shortcuts we could take if we wanted some additional qubits that we didn't care so much about the coherence time on.
Right.
Certainly would let us make them smaller, for example, which can help with some of the layout issues. But it feels like an expensive trade-off to replace a classical resource with a quantum resource.
Right.
I kind of prefer to give you the classical resources that you need.
Yeah, but anyway, so this is very exciting. So what do you expect the volume that we can expect in 5 years or 10 years, the quantum volume?
Well, there's a real question: is quantum volume even the appropriate thing to think about once you start talking about an error-corrected quantum computer? Certainly it's something you could still sort of measure, but it doesn't feel right anymore. It feels like something we may have to move away from and design something new. And I think we're all, our goal is to build a universal quantum computer, and I don't think there's any real expectation we can do that without error correction. So.
That's right. Okay, so I think we're almost finishing the time, and I think we need to get ready for the next panel discussion session. Thank you very much, Oliver, and good luck.
Thank you very much.